Hello everyone, welcome back to Physics Talk. Model 3, describing motion and speed using graphs. Make sure you take good notes on this again. Make sure you draw pictures because all that's going to be important for your physics notebook. Our learning objective today is going to be using graphs to describe speed. And so make sure you pay attention that we're going to look at graphs. So that means you're going to be analyzing, interpreting data. You're going to be looking for patterns. You're looking for scale, proportion, and quantity. And as a reminder from the chapter challenge, remember, you are expected to explain what factors affect following distance, braking distance, and the total stopping distance. And of course, the big factor that affects that is speed. Speed of a car affects that on all of them. And so the question then is, how do we see speed in graphs? So to look at that, let's look at this scenario here where we have a car that's moving at a constant speed. Let's say that car is moving at 50 miles an hour, and that means that for every hour, it's going to travel a very specific distance. Well, that distance will be 50 hours. So the first hour, it'll be 50 miles, the second will be 100, the third will be 150, the fourth will be 200, and the last will be 250. And so you can see that, again, we got equal spacing between these. The question is what we'll look in the graph. Well, if you go to 1, it should be at 50 hours. If you go to 2, it should be at 100. At 3, it should be at 150. And 4, it should be 200. And when we graph that, it looks like a straight line. So in general, anytime you have something moving at constant speed, you will have something that moves along a straight line just like this one. And basically, constant speed means straight line on a position time graph, okay, or a distance time graph. So you get a straight line. And so then when looking at that, we saw in our lab different graphs that we got. So let's make sure we explain it all and understand it. So in this first graph here, we have a horizontal line for the position time graph. This is just like when I was shooting the ceiling wasn't moving. So we say that anytime a graph looks like this, we say the object is at rest. There is no change in position. When we look at graph B, you can see there's a little bit of slope. Hopefully that reminds you at the time when you were walking away from the detector, the motion detector, and you're moving slowly. So typically a person is traveling at a slow speed away from the motion detector when it looks like graph B. For graph C, you can see it's a little steeper. If you remember that one, you're also traveling at a faster speed, also away from the motion detector. If you remember this one right here for number D, that's when a person is actually traveling in the opposite direction. So the slope that looks positive is one direction, the slope that looks negative is the opposite direction, and it's basically constant speed again towards the motion detector. Now, of course, since these are all lines here for A, B, C, and D, those are all constant speed. But what about E? So E is a little different. You experience some of that also in your data. And whenever it's curved like this, that means it's not traveling at a constant speed, so it's a non-constant speed. And actually, for this particular one, the speed is increasing. How do we know this? Well, it turns out if you analyze the data even more, the slope becomes an important part of analyzing the graph. And since slope is rise over run, you remember that whenever we're dealing with slope in math, it was always the rise, which is y2 minus y1, and the run is x2 minus x1. Well, this is actually the symbol for change. And so we have the change in y all over the change in x. Well, what is on the y-axis? Well, it's the distance. So it's really the change in distance all over on the x-axis, the change in time. So when we plug that in, well, do you remember what change in distance over change in time is? Exactly. That is the average speed. So it turns out that the slope here is speed. The slope of a graph for position time graph or distance versus time tells us the speed. And so it's important for you to make that important note. The slope is the speed when looking at a distance versus time graph. Now, so as we look at different types of graphs, here's one for a walker, here's one for a runner, here's one for a biker. Does it make sense that the slope is getting steeper and steeper for each of these? A biker can go much faster than a runner can go much faster than a walker, and the steeper the slope, it means that actually they're moving faster and faster. And if you look at this graph over here, you can see not so steep means slow, a little bit faster for the B. But then when you look at A, which is going backwards, this is a fairly fast one compared to D, but it's going backwards. Negative slope means you're going backwards. So that is basically how we analyze graphs. If you have any questions, one last thing to end here, sorry. Let's say, for instance, you're driving a car and you see a deer on the road. What are you going to do? Well, you're going to drive and make sure you stop. The question is, what happens when you see it at this spot right here, but you then take time to react until you brake when you're at this spot here? Well, we define that distance between these two locations as the reaction distance. It is the distance the vehicle travels and the time it takes the driver to react. You see it here, you finally brake here, this is the time it takes for you to react. The longer your reaction time, the longer this distance will be. And as shown in sample problem number 2, distances can be calculated if given the speed and the time. The distance you travel during the time it takes for you to react is called that reaction distance. So if you have again any questions, that's the end of the lesson for today. Please come to tutoring and we will see you then.